further is, yeah, what are you going to do if you're working with a parameter vector theta that has multiple entries? So the previous example was focusing on a single parameter theta, so that's quite easy or quite straightforward. But what should we do if we have more than one parameter? So then we're going to return here to our example with the log normal distribution and data set B. And we're going to derive a confidence interval for the mean of the log normal distribution. And we know that this mean is expressed as the exponential of mu plus sigma squared divided by 2. So it's a function of two unknown parameters, mu and sigma, for which we can derive the maximum likelihood estimators. And in fact, we already did that in the previous example, so I'm not going to repeat that. So we have here mu hat, we have sigma hat, which we actually calculated, so evaluated for the sample that we observed in dataset B. And in the previous example, we also saw that the estimated covariance matrix for these maximum likelihood that comes with these maximum likelihood estimates, that covariance matrix has the following entries, right? That's what we did in the previous example. And now we need to think about, yeah, what can we do if we look at this delta method? And if we want to apply the reasoning of the delta method on this example, where we have two entries, right? So what are we going to do? Well, what the delta method in this case will require us to do is write down again this function g of the unknown parameters that you want to work with. So here it's the function g of mu and sigma. You see the expression there. And then just like we did with the single parameter, we took the derivatives. Well, here we're also going to put together the vector of first order derivatives. So there will be a first order derivative with respect to mu, and there will be a first order derivative with respect to sigma. So if you work that out, the partial first order derivatives, they are given like this, right? So you can check that for yourself. Of course, we can evaluate them for the concrete sample that we have in dataset B by replacing the mu with its estimate, by replacing the sigma with its estimate. And then we have concrete and numerical values for this vector with the first order partial derivatives of this function g. And what we then need, the second element in this delta method, is what we need was the variance, or in this case, the covariance matrix that comes with our estimators for mu hat and sigma hat. But that's something we already derived in the previous example. So putting all of this together, if you look at the variance estimates that we can obtain for this function g of the unknown parameters mu and sigma, and if we evaluate that whole thing by replacing the mu and the sigma with their actual estimates, evaluated for sample B, then we get the following variance estimate for our mean, the exponential of mu hat plus sigma hat squared divided by 2. And so what I do here is I take this vector with the first order partial derivatives numerically evaluated. I take the covariance matrix that comes with my maximum likelihood estimates, mu hat and sigma hat, and I take again this vector with the first order derivatives of g, right? And so if you see, this is a 1 by 2, this is a 2 by 2, and this is a 2 by 1. So we value in the end, if you work out the matrix and the vector multiplications, you get a 1 by 1. You get one quantity that captures the uncertainty that comes with your estimate here of the mean of the log normal distribution. So having that and using the same reasoning as before, I can write down my confidence interval. So that's gonna rely on this function g of mu hat and sigma hat, which we already had, plus minus 1.96 times the square root of the variance estimate that I just obtained. Yeah. You could also say, yeah, a more traditional confidence interval for the mean would work like this. So what we mean here is that you just take the sample mean of the losses observed, and that you say, if I work with the sample mean, then the variance of this sample mean would be the variance of a single observation divided by n, right? So what you could do there is you could work with this sample standard deviation divided by the square root of n, and that would also give you a confidence interval, a more traditional confidence interval, where you only rely on this sample mean and where you rely on the corresponding variance. So here you would just ignore the fact that you make this distributional assumption, the fact that you assume that your losses are log normally distributed. In the second interval here at the bottom, you would ignore that and you would just say, okay, I need to estimate the mean, so I'm going to work with the sample mean and the sample standard deviation, right? So that would give you, in this case, a wider confidence interval because it's based on less assumptions here. So that's an alternative approach. Yeah, so the first confidence interval is really relying on the fact that we assume a log normal distribution and that we can do all these calculations with the delta method to estimate the mean of the log normal distribution and quantify its uncertainty. And then the confidence interval here at the bottom, that's just directly working on the empirics with the sample mean and the sample standard deviation.